Hello student, I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss isomerism. Last class I have finished nomenclature. Now I am going to discuss isomerism. The phenomenon of existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism. What is isomerism? Then now understand, it is the phenomena of existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism. Such compounds are called as isomers. Now I am telling you a flow chart of isomerism. Isomerism actually is mainly divided into two parts. First is structural isomerism, related to a structural isomerism, and other is stereoisomerism. And further structural isomerism is divided into four. First, chain isomerism. Second, position isomerism. Third, functional group isomerism. And fourth, metamerism. And stereoisomerism is divided into two: geometrical isomerism and optical isomerism. Now I am going to discuss a structural isomerism. Compounds having the same molecular formula but different structures means manner in which atoms are linked are classified as structural isomerism. Again you listen, compounds having the same molecular formula but different structures means manners in which atoms are linked are classified as structural isomerism. Some typical examples of different types of structural isomerism I am telling you now. First is the chain isomerism. I told you this structural formula is divided into four: chain isomerism, position isomerism, functional group isomerism, and metamerism. Then now chain isomerism. When two or more compounds have similar molecular formula but different carbon skeleton, these are referred to as chain isomers. Same molecular formula but different carbon skeletons. These are referred to as chain isomers, and the phenomena is termed as chain isomerism. Example I am telling you: pentane. Pentane and isopentane is the example. Now see, pentane has 5 carbon and isopentane has also 5 carbon. Both have same molecular formula. Total 5 carbon. Here also total 5 carbon. Hydrogen is also same. Number of hydrogen is also same. Number of carbon is also same. But they are differing in skeletons. Means their structure. They are differing in structure. Arrangement of atoms. Then pentane, that is a straight 5 atom chain. Straight CH3, CH2, 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 CH3. First and last CH3, and in the middle CH2, CH2. This is a pentane. But now this can also be arranged as a isopentane. Means now one carbon is a branch, CH3 is in the form of a branch. Then now total carbon is 4. One is a branch, then 4 are in a straight. Means first and last is CH3, and in the middle 2 carbon is there. Then one H removed and its place CH3 came and other CH2. Okay, CH3, first and last CH3, 2 carbon, and 2 carbon is in the middle, 4, and 5th carbon is attached with 2nd carbon as methyl group. Then number of hydrogen and number of carbons are same. Number of hydrogen and number of carbons are same, means molecular formula is same. But here this structural formula is different, chain is different, branch is there. That's why it is called chain isomerism, or both are called chain isomer. This isopentane is also called 2-methyl butane, because 5th carbon went just joined as a branch, as a chain. That's why it is called this isopentane, or you can tell this is the chain isomer. Process is known as chain isomerism. Other example I am telling you, neopentane. Here also these three have same number of carbon: pentane, isopentane, neopentane. Here if you will count the number of carbon and hydrogen, then here also it is 5 and hydrogen is 12. CH3, 4 methyl group is attached. Then 5 carbon and 12 hydrogen. In pentane also, how many carbons are there? 5. And hydrogen, then 3. In the beginning 3, in the last 3 is 6. 3, 6. 6 and in the middle 6. CH2, 3. 12. And in isopentane, again same thing. CH3, then H3, 6. And 3 in the middle, CH3 and CH3. Then 6 and 1, 7 and 2, 9, and 9 and 3, 12. Then everywhere formula is same, chemical formula is same, molecular formula is same, but they are in the different chain. Their structure is different. Then molecular formula same, structural formula different. That is, they are in a different chain, different form. That's why it is called chain isomerism. Now, another structural isomerism is position isomerism. By name, it is clear. Again, molecular formula will be the same, but they will differ in position. When 2 or more compounds differ in the position of substituent atom or functional group on the carbon skeleton, they are called position isomers. Again I am telling you, when 2 or more compounds differ in the position of substituent atom or functional group on the carbon skeleton, they are called position isomers, and the phenomenon is termed as position isomerism. For example, I am telling you, molecular formula C3H8O. Now two forms are there, two isomers are there. Both have same molecular formula. Both have a same molecular formula, but they are differing in the, you can say, position of OH group. C3H8O. This is actually propane 1-all. Propane 1-all means propanol. You can tell propanol, alcohol. OH group is attached. or this, but this propanol you can write propane 2 all also. In the beginning it was in one isomer OH is attached with first carbon. Now in second isomer OH is attached with second carbon. Then in the place of OH, H gone there, and from that carbon, from where H gone, there OH attached. Then see, this propane 1 all and propane 2 all are the isomers of C3H8O. Isomer means same. Yeah, just to keep in mind. Iso means same. Then I told about the position isomerism. Now third structural isomerism, that is the functional group isomerism. Functional group isomerism. Here again you can understand that again molecular formula will be the same, but they can form different functional group. Okay, both isomer can have different functional group. Two or more compounds having the same molecular formula but different functional group are called functional isomers, and this phenomena is termed as functional group isomerism. Here again every time same thing, molecular formula is same, structure formula is different, but here they have different functional group. Then this type of isomers are called functional isomers, and this phenomena is termed as functional group isomerism. Example I am telling you. For example, the molecular formula C3H6O represent an aldehyde. C3H6O represent an aldehyde and a ketone. Okay, this. Then here you will see that molecular formula is same but functional group is different. Then now you can see propanone means CO group is there. CO is the carbonyl group. Then here CH3, three carbons are there. Then the beginning CH3, last CH3, in the middle only one carbon is there, that is attached with one oxygen. Then this is the CO group, that is called carbonyl group, and other is propanal aldehyde, that is called propanal, Al. Propanal. Then now this CH3, CH2, CHO. Now can you see in both a compound group is different. One is ketonic group or carbonyl group, you can tell, CO group, that is acetone, CH3, CO, CH3, this is called acetone. And propanal, Al means aldehyde, and the end CH3, CH2, CHO group is there. Then both have same molecular formula but different group, that's why different functional group, that's why it is called functional isomerism. Now next structural isomers, that is the metamerism. Then metamerism, it arises due to different alkyl chain on either side of the functional group. This metamerism, it arises due to different alkyl chains on either side of functional group in the molecular formula. For example, C4H10O represents methoxypropane. Then here you can see methoxypropane means CH3O CH3O C3H7. One compound having same molecular formula and other is ethoxyethane. Then see O is in the middle. O is in the middle. One side of O is CH3, other side is C3H2. And another example, that is the isomers C4H10O. Then first is CH3O against C3H7. They have different alkyl group. One side methyl group, other side propyl group. And other you can see other compound C2H5 means ethyl group. Both side is ethyl group. O in the middle means ether. Di is also called diethyl ether. C2H5 again O in the middle, again C2H5 diethyl ether. And other isomer is CH3O C3H2 means here one side methyl group is there, other side propyl group is there. Okay, then these two compounds are isomers and this is called metamerism. Processes both are metamers, and process is called metamerism. Okay, keep in mind example is C4H10O. Molecular formula for both compound is same, but they are differing. They have different alkyl group in both compound, in both isomer. This I have discussed about the structural isomerism. Now I am going, actually a stereoisomer is not at lower classes. It is for higher classes. I will discuss when I will discuss for higher classes. Now here simply the compounds that have the same constitution and sequence of covalent bonds but differ in relative position of their atoms or groups in a space are called stereoisomers. Again you listen. This is also molecular formula will be the same. That is the common in all isomers. Then here the compounds that have the same constitution and sequence of covalent bonds, all similarities is there. Molecular formula is there, and how many bonds are, that is also same type of bond is there. Yeah. That is the constitution is the same. Constitution and sequence of covalent bond are same. But what they differ? But differ in relative position of their atoms or groups in a space. Then this type of isomers are called stereoisomer. In a space, how they are arranged, they will differ in that you can say relative position of their atoms or groups in a space, how they are arranged, they differ in that. All things will be sequence of bond will be also same. Atom will be also the same. All things are same. Molecular formula same. Sequence of covalent bond is same. But how they are arranged in a space at what angles, there they will differ. All things will be the same. In a space, their arrangement in position, there they will change. Relative position, their difference will be, they will differ in relative position in a space. Then this type of isomers are called stereoisomers. This special types of isomers is called as stereoisomerism. This special type of isomerism is called as stereoisomerism. and can be classified as geometrical and optical isomerism. Geometrical isomerism and optical isomerism. Geometry means they will differ in angle. One type is there, they will differ in angle. I am telling just I will not go in details in that. At right place I will discuss. But geometrical isomerism means here that they will differ in angles in a space. And optical isomerism, optical means light. Then optical isomers they will behave differently with light. Their behavior will be, they have difference in behavior with light, optics. Then that's why it is called optical isomerism, and isomers are called optical isomer. Now I am going to discuss covalent, not this covalent. I am going to discuss now that fundamental concept in organic reaction mechanism. Reaction mechanism, what is the reaction mechanism that I am going to discuss? Reaction mechanism of organic compound, or contain fundamental concept in organic reaction. Every reaction has some steps, how they will give the product. From reactant to product, they will go in some steps. Then that steps are called steps involved in the reaction. That is called reaction mechanism. How directly it will not give the product. If you will study, you will find a step by step they will react and they will give the final product. Then these steps are called mechanism, organic reaction mechanism. Their concept now I am going to tell you. Then what is actually this concept that I am telling you? In an organic reaction, the organic molecules, also called substrate. Organic molecules are also called substrate. Then these molecules in an organic reaction, the organic molecules reacts with an appropriate attacking reagent and lead to the formation of one or more intermediate and finally products. Then here one or more intermediates, means before giving the product they will form maybe one or two intermediates. Then these are the actually sequence, how they will form the these intermediates and how intermediate will give the product step by step. That is called mechanism, organic reaction mechanism. Means reactant to product, directly you are writing, but actually it will give in the middle some intermediate it will form for short period, and that will convert to the product. Okay. Then you can show like that organic molecules plus attacking reagent. It will give intermediates, and again this intermediate in next step it will give products. And this intermediate that is also you can tell sometimes byproduct. This not there means this intermediate can give some byproduct also and main product also. Means reactant will give intermediate products, and after that it will give final product. Okay. Then substrate is that what is the substrate? I have told you these are organic molecules. Substrate is that reactant which supplies carbon to the new bond, and the other reactant is called reactant. other reactant is called reagent. Two will be there, two reactant will be there. Then one will supply the carbon for the reaction, and other reactant will be called reagent. Other will be called reagent. Okay, substrate is that reactant which supplies carbon to the new bond, and the other reactant is called reagent. Okay, then reagent and substrate both will react. Both are organic molecules. In both the reactants, if both the reactants supply carbon to the new bond, then choice is arbitrary, and in that case the molecules on which these things attention is focused, that is called substrate, where you are giving importance, that is called substrate, where you are giving attention, that is called, that molecule is called substrate. Okay, then simply anyone you can give that, you can tell the substrate. That molecules on which attention is focused is called substrate. In such a reaction, a covalent bond between two carbon atom or a carbon and some other atom is broken and a new bond is formed. Here, this is the only important thing. In all reaction, either organic or inorganic, whatever be, particularly organic I am talking now here, that first old bond will be broken and then a new bond will be formed. Old bond will be broken and new bond will be formed. Then it will give the product. Then in such a reaction, a covalent bond between two carbon atoms or a carbon and some other atom is broken and a new bond is formed. A sequential account, listen carefully, a sequential account of each step describing details of electron movement, energetics during bond cleavage and bond formation, and the rates of transformation of reactants into products is called reaction mechanism. Reaction mechanism. Okay, here during the bond, to break the bond, energy is required. To form the new compound, energy is required. Then that for the breaking energy is required, and for making new bond, when it will give the product, a bond will be formed. There also energy is required. Then at what speed or rate of the reaction you can tell, how much time it takes in breaking the old bond and making the new bond for the product. Then that kinetics, that is also called rate of reaction, is called kinetics. How fast or how slow reaction is going on. Then all this sequence means a substantial account of each step describing details of electron movement. Energetics means how electron is moving, how energy it is releasing or taking, whatever be, during bond cleavage means bond breaking and bond formation, and the rate of transformation, at what rate it is converting from reactant to product. That is called reaction mechanism. Then in reaction mechanism, all things is discussed. Breaking of bond, formation of intermediates, and then formation of product from the intermediate, formation of product, and during this how much energy is required, how much energy was involved, and how fast reaction takes place. How fast reaction takes place means kinetics also you have to study, is considered. Then this is called actually reaction mechanism. One more time I am telling you, question is asked, what is the reaction mechanism? Then a sequential account of each step describing details of electron movement. In all reaction there will be movement of electron. Keep in mind, everywhere, wherever reaction is there, movement of electron is there. Then a sequential accounts of each step describing details of electron movement, energetics during bond cleavage and bond formation, and the rate of transformation of reactants into product is referred to as reaction mechanism. The knowledge of reaction mechanism helps in understanding the reactivity of organic compounds and in planning a strategy for their synthesis. This will give you idea that understanding of reactivity, first things, understanding of reactivity of organic compounds and in planning a strategy for their synthesis, how you can synthesis in more quantity, or you can, how you want to manufacture means large quantity, then you can make plan. Okay. Now I am going to tell you fission of a covalent bond. These are the steps actually that principles that explain how this reaction takes place. Reaction, how does reaction takes place? How will you understand? Then step by step all things you have to understand. Then in that if you want to study organic reaction mechanism, then you have to understand fission of a covalent bond. Organic compounds, all organic compounds have a covalent bond. Then cleavage of this covalent bond means fission. Also you can tell fission of a covalent bond, breaking of covalent bond. Then there are two types of you can say fission. A covalent bond get cleaved means can be broken either by heterolytic cleavage or by homolytic cleavage. There are two ways to break the bond. One is called heterolytic cleavage and second is called homolytic cleavage. Hetero means different, homo means same. Now one by one you can understand. In heterolytic cleavage, the bond breaks in such a fashion that the shared pair of electrons remains with one of the fragments. So it is very easy, both are very easy. When a covalent bond is breaking, then when bond will be broken, in one bond two electron is there. Then when bond breaks, then two electrons, where it will go? Then what is the two possibilities there? That in one possibility is that both electron will be taken by any one fragment. Suppose it is broken into two parts. Then when bond will break, then both electron will be taken by any one fragments, any one part. Correct? This is the one case. Then this is the case of heterocyclic. Any one fragment will take both electron. Then obviously when they will take both electron, then that fragment will be negative. It will be negative and other will be positive because they lost the electron. Then they will be positive. Who is losing electron? They will have positive. Then they will form carbocation. And other fragments who have taken electron, that is called anion. Anion negatively charged. That will be negatively charged. Okay, I will tell you about the homolytic also. Easily you can understand. Now, just with example, you understand that after heterolysis, heterolytic process is called heterolysis. After heterolysis, one atom has a sextet because that they were having 8 electrons. When bond is forming, when covalent, before breaking the covalent bond, octet was complete. Atom octet was complete, but one pair of electron is taken by the other. Then now after losing 2 electron, they will have sextet, 6 electron. Okay, sextet, and means octet became sextet. One lone pair is less, and a negative charge. Okay, electron structure after heterolysis, one atom has a sextet electronic structure, means 6, and a positive charge, because they have lost the electrons, and the other a valence octet with an at least one lone pair and a negative charge, means one fractional will get 2 electron plus negative charge. Because they have taken an electron, that's why automatically negative will be there. Another will be 6 electron and positive charge. These things only is important in heterolytic cleavage. Okay. Example I am telling you. Suppose methyl bromide is there. Methyl bromide, CH3Br. Then bromine is electronegative. Maybe bromine, maybe chlorine, maybe iodine, all are electronegative. Then what is their any electronegative, what is their role? They will attract the electron. This will take the electron, okay, of the bond. Of the broken bond, electron will be taken by electronegative atom. Here bromine will take that electron. Okay, and this bromine will take a distant electron. Then bromine will have negative charge and CH3 will have positive charge. Okay, a species having a carbon atom possessing sextet of electron and a positive charge is called carbocation. Okay, and earlier it was called carbonium ion, carbonium. Now it is called carbocation because they have carbon has positive charge. That's why carbocation. In a general way, you are telling cation, having positive species, having positive charge is called cation. But here in organic chemistry, carbon has positive charge. That's why it's a carbocation. And earlier it was called carbonium. Then this I have told you. The CH3 ion is known as methyl cation or methyl carbonium ion. Carbocation are classified as primary, secondary and tertiary depending on whether 1, 2 or 3 carbons are directly attached to the positively charged carbon. Positively charged carbon, if they are attached to 1 carbon, then primary. If they are attached with 2 carbon, then secondary. If attached with 3 carbon, then tertiary. Okay. First, this I told you that primary, secondary and tertiary depending on the whether 1, 2 or 3 carbons are directly attached to the positively charged carbon. Some other examples of carbocation are, you can take CH3 CH2, CH3 CH2, CH2 is 1 plus, means ethyl cation, also called ethyl cation. A primary carbocation because this CH2 is attached with 1 carbon, CH3, it is attached with CH3 means 1 carbon. then it is a primary. Ethyl cation, a primary carbocation. If two methyl group is attached, means two carbon is attached, then it's called isopropyl. Isopropyl. Okay. A secondary carbocation is also called secondary. And if three carbons are attached, means three methyl group is attached, CH3 to the positively carbon, then it is called tertiary butyl cation. Tertiary butyl cation, because total 3 is attached with fourth one. That's why total tertiary butyl cation. A tertiary carbocation, also called a tertiary carbocation. Carbocations are highly unstable. Now another important point is this: carbocations are highly unstable and reactive. Carbocations are highly unstable and reactive species. Alkyl groups directly attached to the positively charged carbons stabilizes the carbocation, because methyl group, when they will attach, then they are lacking, they have only 6 electrons. Means carbocation, that carbon will have only 6 electrons. Then methyl group, when it will attach, then they will supply the electron. If one carbon is attached, then it will stabilize that carbon, C plus carbocation, it will stabilize to that carbon, C plus. If two are attached, means secondary, then further it will be stabilized. If three are attached, then further it will stabilize. Means tertiary, if tertiary 3 carbons are attached to that carbon, C plus, then that C plus will be stabilized. This is the important. Alkyl groups directly attached to the positively charged carbon stabilize the carbocation due to inductive and hyper conjugation effect. This due to these two effect, I will tell you later on, inductive effect and hyperconjugation effect. Due to these two effect, they will stabilize the carbocation. Okay. Now the observed order of carbocation stability I am telling you. It is asked in examination. Then already I told you, highest is CH3. If CH3 plus is there, carbocation is there, but methyl is there, C plus and CH3. C plus H3 is attached, CH3 having 1 plus. Then this is the weakest. Then after that, if CH2 group is attached with this CH3 group is attached, then this will be, if with this CH3, CH2 is attached, not with this CH3, with this CH3, this I am telling you now sequence, CH plus CH3 is there, then plus CH3 is less, it is less stable than CH3 CH2, means one carbon is attached, means methyl is less stable than ethyl carbocation. Methyl carbocation is less stable than ethyl, and ethyl is less stable than dimethyl CH, means CH3 whole to CH. Actually, plus CH3 was there. In that, 1H is going to be removed. Or replaced by other CH3. Then plus CH3 was there. Then 1H gone. In the place of another CH3 came. Then now it became CH3 CH2 1 plus. Now from the CH3 another H is also, it will also go. Then now it will 3 carbon, total 3 will be there. 2 carbon attached. Then that will be stabler than 2. Means CH3 is less stable. CH3 methyl carbocation is less stable than ethyl. Ethyl is less than propyl, and propyl is less than butyl. Okay, this is the sequence. Means CH3 is less than CH3 CH2, CH3 CH2 is less than CH3 whole 2 CH, and this is less than CH3 whole 3 C. These carbocations have trigonal planar shape. These carbocations have trigonal planar shape with positively charged carbon, and they are sp2 hybridized. This also you remember. All these can say carbocation what I told you are, means carbon is sp2 hybridized. In all, carbon is being sp2 hybridized. Thus the shape of methyl group, or a methyl you can say CH3 plus, may be considered as being derived from the overlap of three equivalents S, 1s and 2p of carbon. There carbon has three these orbitals of carbon has overlapped. 1s and 2p are hybridized. That's why it is called sp2 hybridized orbitals. Okay, sp2 hybridized orbitals. This I have told you. This is very, very important. Question is asked. And now here again further each bond, 3 bonds will be there. sp3 means total, sp2 means total it can form 3 bond, sp2 total 3, s and 2p, sp2 means 3 orbitals are there, hence it can make 3 bond. Each bond may be represented as sp2h sigma bond. Carbon has 3 orbitals, sp2, 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 then it can make a bond with 3 hydrogen, and sp2h, sp2h, sp2h sigma bond. And fourth orbital is unhybridized. Fourth orbital is unhybridized. Okay, and then there the remaining carbon orbitals is perpendicular to the molecular plane and contains no electrons. Fourth one I am talking about, means the remaining carbon orbital, that is the fourth one, is perpendicular to the molecular plane and contains no electrons. Okay, means fourth orbital p orbital has not taken part in the hybridization. It was not having any electron. Okay, this I told about the heterolytic cleavage. Heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. It is not necessary that always fluoride, chloride, bromide will be attached with the carbon. Sometimes other carbon will be also attached. Okay, then in that situation, if a bond will be broken, then any one carbon will have can say that shared that two electrons. Two electrons may have any one carbon. Okay, then it is not necessary that only hydrogen will be there. The heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. For example, when a group Z attached to the carbon leaves without electron pair, the methyl anion is formed. Okay, example I am telling you, when a group Z is attached, suppose with the methyl group Z is attached, when group Z attached to the carbon leaves without electron pair, means from the Z was having electron, that is taken by methyl group, then methine will be negative, then methyl will be negative and Z will be positive, and Z will be positive. Then electron pair will be with methyl group, and it is called methyl anion, just like methyl carbocation. Methyl cation is now it is methyl anion because it has taken the electron. The methyl anion is formed. Such a carbon species carrying a negative charge on carbon atom is called carbanion. Carbanion. Okay. Again you remember that such a carbon species carrying a negative charge on carbon atom is called carbanion. Okay. Carbanion are also unstable and reactive species. The organic reaction which proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reaction. The organic reaction which proceed through heterolytic bond cleavage are called ionic or heteropolar or simply just polar reaction. Now come to the homo cleavage. It is very easy. Both are easy only. In homolytic cleavage, what will happen? That when bond will break, covalent bond will break, then both carbon will take one electron. Generally, this will happen in sunlight, in presence of UV light. Okay. Then both shared electron will be taken by one. Both have shared during bond formation. Now both will take one electron. Then this process is called actually homolytic cleavage. No positive charge, no negative charge. One electron they have taken. Okay, and it is called radical. This is called radical, and it will be very, very reactive. Okay, this is the main things of heterolytic cleavage. Now I am telling you little details. In homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atoms. Thus, in homolytic cleavage, the movement of a single electron takes place instead of an electron pair. Here there is no question of movement of electron pair. Single electron both will take, both carbon. The single electron movement, that is shown by how we will represent. This is the new thing you should understand. How will you show this movement of electron, single electron movement? The single electron movement is shown by a half-headed, or also you can tell fish hook. Also you can tell curved arrow. Its name is half-headed or fish hook. Fishermen, they will use the hook to catch the fish. Then this structure will like that way only. Half-headed, also you can tell fish hook, also you can tell curved arrow. Such cleavage results in the formation of a neutral species, atom or group, neutral, no positive, no negative, which contains an unpaired electron, only one unpaired electron. These species are called free radicals. Like carbocations and carboanions, free radicals are also very reactive. And this, suppose a molecule is RX molecule is there. if you want to represent how homolytic cleavage is going on, then Rx, X is halogen group, maybe fluorine, chlorine, bromine, iodine. Then X you can consider Rx. Then between R and X, two electron is there in this bond. Then you can make a two curved arrow. Two curved arrow you can make, each for one electron. Half I told you, half-headed or fish hook or curved arrow. Two arrow you have to make half-headed. One towards one carbon and other towards other carbon. Both electrons are there. One electron will go to the right, other electron will go to the left. Then that you can show by that curve arrow, half-headed or fish hook. One direction, both will be opposite direction. This then Rx will break into R and X, R plus X, and R will have one electron, X will have one electron, and both are called free radical, alkyl free radical. If you can say one electron is taken by X, other electron taken by R, then R will be alkyl. It will be called alkyl free radical. Alkyl radicals are classified as primary, secondary and tertiary. Already I have told you. If one carbon is attached, if only one electron is attached with primary, then that is the primary alkyl radical. If with two carbon one electron is there, then secondary. If with three carbon one electron is there, tertiary. Okay. Alkyl radicals stability increases. Alkyl radical stability increases as we proceed from primary to tertiary. Tertiary will be strongest, primary will be weakest. Then you can understand, question is asked that CH3 methyl free radical is unstable or weaker than ethyl radical. Ethyl radical is weaker than isopropyl radical, and isopropyl means CH3 whole 2, CH and CH3 whole 2, that is the isopropyl, and isopropyl radical is weaker than tertiary butyl free radical. Okay. Organic reactions which proceed by homolytic fission are called free radical homolytic or non-polar reaction. Non-polar means now understood that no charge. Non-polar, no charge. Okay. Polar means having some charge. Having maybe less, but will have charge, because here is a non-polar, because bond broken, but one radical both have taken. That's why no charge development. This is called non-polar. Now I am stopping only here. Next class I will discuss other terms. Thank you.